Uh, Professor Karpyn, thank you for that very interesting presentation. It was really informative and educational even for me. I always love to learn about energy and fuels and oil and gas, energy storage in general. We have quite a few questions from our audience today and a couple of questions from us at ACS as well. So, if you do not mind answering a few of these, I can ask a few.
Yeah, please, please.
Yeah. So, my first question has to do with uh, the kind of measurements that you've done. What I remember from my studies is that all of these pore sizes are quite. I mean, there's a huge distribution of pore sizes, but let's assume that mean free path at standard temperature and pressure for, let's say, carbon dioxide or methane is around 100, 105 nanometer or something like that. Then wouldn't it be that the Knudsen diffusion dominates when the pore size is below this 100 or 105 nanometer? And I would believe that increases the effective surface area. So did your group ever look into this particular probability?
Thank you, Kaushik, for the question. Absolutely, it's absolutely true that when um, the pores get small enough that they begin to get within the range of mean free path for the molecules of the fluids that are inside, then Knudsen diffusion begins to dominate. We go from a pressure viscous dominated type of flow to more diffusion type of dominated flow. Um, that that is something that we do know. These experiments were in particular not to intend to look at transport per se, and that's why we looked at equilibrium conditions from initial to final equilibrium conditions. But if we were to model, and we've done some experiments in that range as well to look at a transport per se, and then we would have to take that into consideration in our estimates of conductivity through the samples.
Thank you, Professor. My next question has to do, it's a more general question. What are some of the challenges associated with recovery of stored gases like methane and hydrogen from these shale formations?
Kosha, can you repeat your question, please? Because I think the audio, broke up, was breaking up a little bit for me and couldn't pick
Yeah,
up the question.
let me just repeat. What are some of the challenges associated with recovering, that is, valorizing stored methane and hydrogen from these shale formations?
Okay, some of the challenges in valorizing the assessment of the gas in place, I think, for
Yeah,
these
yes,
formations.
yes.
And I think you are talking in terms of the storage of natural gas or you're thinking of this from the point of view of production of hydrocarbons, right? I think your question is that's how it's the intent of your question. I think that let me try to address if I'm not addressing your point, please let me know. But some of the challenges here in assessing the value of the gas in place is this estimation of how much is it really in place. We know, these estimates of the areal extent of these formations. We can take, localized samples to estimate porosity. We can make volumetric, first order volumetric assessments of how much gas is in place in these formations prior to production. But oftentimes our estimates of how much gas is in place is subject to estimations because of the inherent complexity of these systems, the fact that there's significant amount of nanoporosity and that makes it more challenging to be able to estimate how much it's in place. And I think an important piece here as well is this effect of how thermodynamic properties of the fluids are altered by this confinement, and that creates another complexity of uncertainty in terms of being able to assess initial gas in place when it comes to be able to get to production. The tables turn then in the uncertainty and the complexity of that assessment when we now try to think in terms of underground storage, because then, similar questions of, how much, volume can we store, under what conditions, and what thermodynamic properties we attribute to those gases. And that's in part what we try to address with this work, the idea that in situ conditions of pressure and temperature in the reservoir are not sufficient to represent the density of the gases that we put in these materials because of the confined, characteristics that they have.
Thank you, Professor. Our next question comes from the audience. It's related to slide number 6 in your presentation.
Yeah, the experimental setup.
The question here is, what could be a possible explanation for differences observed between the uptake of argon and helium? One would expect that they would be closer to each other than methane, for example.
Yes, that's a very good observation. I would have expected the same. Argon is certainly a larger molecule than helium, but the uptake that we observe make argon and methane much more comparable in that additional uptake. I honestly don't have the answer to that distinction, but I agree with the observation that intuitively you would think that if the attribution of this uptake is strictly related to the relative size of the gas molecules and the pore space available and the interactions that you would expect, then the proportionality is not linearly correlated, if I would say. So it's an interesting observation. I completely agree. I don't have a good answer, but I note the observation from the person that make the question.
Just as an addendum to that question, can we assume that the differences have anything to do with the physicochemical properties of the gas itself and any potential chemical affinity with the molecular composition of the rocks?
Yes, yes. There are potentially multiple sources for this, and I think this is one of the challenges of the work, that we have very compelling evidence of the manifestation of this densification and how much more gas we're able to see residing in these samples. But the the relative contribution of different potential factors that would affect it is hard to parse out. I would think that, one possibility is, like it's mentioned, the thermodynamic properties of the gas itself. If you have different, critical conditions, if you have different, phase behavior, conditions where maybe some of this densification or these interactions render conditions that are prone to confinement induce capillary condensation. And that might be more likely for one gas than the other, perhaps, more likely for something like, one gas over the other. And that all of that plays into this bundle of impact, creating this excess manifestation of gas intake.
Thank you, Professor. The next question from the audience is regarding slide number 12 in your presentation. The question is, does the organic content that was quantified in your analysis include or exclude sulfur?
If it excludes sulfur?
Yeah. Yes.
I believe that it excludes sulfur.
The next question has to do with how your group has estimated the porosity of each voxel. Since the scan resolution is about 16 microns, it might not be enough to fully resolve the pore space of the shales.
True. Yes, the resolution of the scanner, the voxel resolution is not enough to resolve explicitly pore space to create a binary distribution of pores and rocks. This is not suitable for any of these shale samples. For the shale samples that have a larger porosity, the back end, for the back end core, we were able to create an independent experiment where we saturated the sample with a liquid for an immiscible fluid, and then through image subtraction, we're able to do a distribution or estimate a distribution of porosity by voxel. But that requires the saturation with an immiscible with a incompressible fluid to be able to make that measurement. In some of the other cases, we had to, because the samples were so tight, it wasn't viable to introduce an incompressible fluid into the rock to make these independent measurements of porosity. What we did is we had to rely on approximations of porosity based uniquely on the dry scans. So the assumption that we're making there is that the attenuation coefficients for each voxel from the dry scans are a reasonable approximation of the density of the material, and the density of the material locally maps to porosity. So that's how we looked at different approaches and compare with some other you know estimates or reports of porosity values for these rocks to have at least a frame of reference. But we did different things for some of the different samples. In some cases, ideally, the best approach is to independently try to, get a, fluid saturated with a tagged water or solution that would allow us to obtain porosities by voxel throughout the entire sample and in space.
Thank you, Professor. The next question comes from our audience. One of our members attending today has asked, which of these three shale reserves have high methane content, and can we assume there is any kind of correlation between methane storage and carbon dioxide storage capacity?
That's a good, I think that's a reasonable extension of the impact of one versus the other. We didn't do CO2 in our collection of gases that we tried, but if I were to, try to estimate, I think for CO2 it would be comparable to methane.
Thank you, Professor. So there's a different kind of question from one of our members attending today. Since these are porous materials to begin with, whether any of them extracted on a smaller scale can be used for energy storage applications in a more electrical context like capacitors or batteries. Can we use any of these rock formation materials to say make a sodium ion battery or something like?
Yes. I like the creative thinking that comes with that. I think it would be very challenging to use this natural material to engineer these types of systems. I think it'd probably be more convenient to try to manufacture materials that mimic some of the qualities of these samples. It'd be challenging because these rocks are also very brittle materials. It's extremely difficult to size them in shapes that you would want to use for different things. So they're extremely brittle materials. So that's a huge disadvantage when you try to think about engineering different components, with this material. But I think that we have the capabilities of manufacturing, smart materials, probably even smarter than the shells, but use some of this understanding to mimic or engineer the properties or the behavior that we want to see reflected in them.
Thank you, Professor. The next question comes from
Sorry, Kaushik, to jump in. but we might be able to take one more question.
Yes, this is the last.
Okay, thank you.
Okay. So, Professor Karpyn, the next question comes from our audience. Uh, it 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 has to do with asking whether your group has done any kind of dynamic experiments in these studies and any tests in the presence of brine.
Great. Thank you. So great collection of questions, I have to say. All of them, reveal a good, you know, thought process and very relevant, for the work that I'm presenting today. So I've enjoyed the depth of the questions. This work itself, as you see, we conducted these pressure decline experiments in the scanner. I presented, for the sake of this, talk, only the initial and final equilibrated conditions. But we do have dynamic scanning of the intermediate stages, and they're published in the literature. Those can be found. But we dynamically were able in the process, because it's a slow process of diffusion dominated process. X-ray ACT allows for temporal scanning. This is because it's not a process that happens too fast. So we do it over days, to be able to monitor that dynamic process, and that presents a really interesting, data set for simulation purposes, because then you can try to look for the physical models that best represent the concentration profiles and the timeline of the experiment. We have not performed this particular experiment in with brine, but I remember I've done some prior work that was motivated by, this idea of soak in time. When we do hydraulic fracturing in ultra tight formations and there's water utilized for that hydraulic fracturing, we have to conduct some experiments to try to represent the hindrance that water creates for the gas that ultimately you want to produce. So it's been a different type of work. We didn't do brine saturation or initial conditions or even connect water in this particular collection of experiments with these shells, but I had some other experiments and collection of things that we've done in our research group that looks at water penetrating the rock and waiting over time to see how recoverable is the effective permeability of the gas that ultimately you want to produce when you have this water blockage.
Thank you, Professor. With that, we conclude our Q&A session. We have many people here as attendees from industry and academia, all interested in working in this field. And I would request you to deliver any closing remarks to our audience today for people who are interested to do further work and explore new horizons in this field.
Absolutely. I wanted to say thank you for everybody. It's it's very humbling to see all the positive feedback, the depth of the questions. I appreciate the opportunity of being part of this forum. I'm more than happy to talk about this more in depth. I'm findable. You can search for me at Penn State. You'll be able to find me. Feel free to send a follow-up communication if there are questions that you want to dig a little bit deeper on, or maybe establish collaboration or answer questions that you might have to enhance the work that you're doing. I really love this type of forums where we get to share science and accelerates each other's science by contributing and sharing some of the work that we're doing. So thank you for facilitating it.